Assalamualaikum and good morning to Dr. Radzi, our GAs and fellow classmates. Today, my team and I will be doing a virtual CMOS fabrication using ATEC process. CMOS stands for Complementary Metal Oxide Semiconductor. Each MOSFET has two terminals, a source, and a drain. With enough applied voltage, electrons can flow between the two terminals. It is called complementary because each transistor consists of both P and N-type semiconductors. We will be going through the various steps in fabricating a CMOS device, from thermal processes to etching. The first part of thermal process is oxidation. Oxidation is growing a layer of silicon dioxide to protect the silicon surface. A silicon dioxide is a stable and strong dielectric material. It is easily formed in high temperatures. Thermal processes are conducted in diffusion furnaces, which consist of two types, vertical and horizontal. The parts are made of fused quartz because they are stable at high temperatures. The basic components of a diffusion furnace include the control system, which is a computer connected to many microcontrollers, a gas delivery system, a loading system, an exhaust system, and a processing tube. Oxidation is adding oxygen to silicon wafer to form silicon dioxide. Silicon is very reactive to oxygen, and upon contact, they react immediately to form native oxide, a very thin layer of silicon dioxide. The silicon dioxide is dense and fully covers the silicon surface, preventing the oxygen from further diffusing into the silicon. Higher temperature must be applied to make the oxygen molecules move faster for more diffusion. So, the oxygen will penetrate through the native oxide and into the silicon, which allows for further oxidation. Thus, the silicon dioxide grows into the silicon even more. With higher temperature, we have quicker oxide growth and higher quality oxide. Oxidation is a very slow process, so it is done in batch processes with 100 and 200 wafers at a time. Next, pre-oxidation cleaning must be done to avoid crystallization, which can lead to impurities and moisture. It is done through wet cleaning process by submerging the wafers in strong oxidizers. Afterwards, the wafers are rinsed with DI water and dried using a spin dryer. Hydrofluoric acid is used to remove native oxide. Oxidation rate. When the oxide layer is thin, under 500 angstrom, the oxygen continues to diffuse into the silicon with ease, and therefore the silicon dioxide grows linearly with growth time. When the oxide layer is thicker, the diffusion process slows down because of the collisions between the atoms in the oxide layer. Thus, the diffusion limited regime is slower than the linear growth regime. Oxidation rate is affected by many factors, especially by temperature. There are two types of oxidation, wet and dry. For wet oxidation, water is used as oxygen source, and the oxide is called steam oxide. In high temperatures, water will dissociate into hydroxide, which diffuses faster in silicon dioxide. So, wet oxidation has a higher oxidation rate, and it is used for growing thick oxide. It uses a pyrogenic steam system, which burns hydrogen at the entrance of the tube to form water vapor. For dry oxidation, high purity oxygen is used as the oxygen source, and hydrochloric acid is used to reduce mobile ions such as sodium. It has a lower growth rate, so it is used for thin oxides under 50 angstroms. However, it produces a better oxide film quality. According to AdTech run card, wet oxidation is conducted for first field oxidation after wafer preparation. This shows the flow of the wet oxidation. Firstly, it is ideal with purged nitrogen, and then it is ideal with processed nitrogen. Afterwards, oxygen is ramped up, and the wafer bolts are pushed into the process tube. Temperature is increased until stabilized, and oxygen is increased until stabilized. Turn on hydrogen, and then steam oxidation with hydrogen and oxidation. Afterwards, turn on processed nitrogen and turn off oxygen and hydrogen. Temperature is turned down and the wafer bolts are pushed out of the process tube. It is ideal with processed nitrogen, and then the whole process is repeated again. Lastly, it is ideal with purged nitrogen. Meanwhile, dry oxidation is conducted for second gate oxidation after second gate masking. This shows the flow of the dry oxidation sequence. Instead of water, oxygen and hydrochloric acid is used. During idle time, the temperature is around 850 degrees Celsius, while inside the flat zone it is 1000 degrees Celsius. After the wafer bolts are pushed in, the temperature is ramped up at a rate of 10 degrees Celsius per minute to reduce thermal stress. After oxidation is done, we must measure the oxide thickness and uniformity using various methods such as ellipsometry, color charts, and spectroreflectometry. For the gate oxide, we must also measure the breakdown voltage and fixed charge.
Good morning, my name is Dharmini and I will be presenting on the thermal processes. So what is a thermal process? Thermal process occurs in a high temperature furnace called the diffusion furnace. This is called so because it was extensively used in the diffusion doping processes in the early years of the semiconductor industry. A rapid thermal processing or RTP is a semiconductor manufacturing process which heats the silicon wafers to high temperatures, which is over 1000 degrees Celsius, on a time scale of several seconds or less than that. During cooling, however, wafer temperatures must be brought down slowly to prevent dislocations and wafer breakage due to the thermal shock. Moving on, we are going to be discussing about what is actually diffusion. Diffusion is the movement of impure atoms in a semiconductor material at high temperatures. Although diffusion can also be an unwanted parasitic effect because it takes place during all high temperature processes. Moving on, the driving force of diffusion is the concentration gradient. The diffusion time and temperature determines the depth of dopant penetration. Diffusion is used to form the source, drain, and channel regions in a MOS transistor. Moving on, every process is bound to have its limitations, so does diffusion. So let's look at diffusion's limitations. Diffusion is an isotropic process and always dopes underneath the masking oxide. It cannot independently control junction depth and dopant concentration. It is able to be replaced by ion implantation due to the less process control. One of its advantages and why is it still being used is because of its drive-in for well formation and is used for well implantation drive-in. Moving on, thermal budget. Thermal budget determines the time and temperature of the post-implantation thermal processes. So the equation that I've inserted is to simplify the situation that happens where the dopant atoms diffuse fast at high temperatures. So what are the factors is that smaller device geometry contributes to less room for dopal thermal diffusion, which contributes to a less thermal budget. Moving on, dopant measurement. This can be used by using the 4-point probe, which I have inserted in a diagram there to show you. The blue colored highlighted sticks there is the 4-point probe, which is used as the doping measurement. So what you see in front here is the flow of processes where we prepare our wafer. So figure 1 shows a clean wafer, figure 2 shows that we are undergoing the process of oxidation, and figure 3 shows the patterning of the doped area, and figure 4 shows the etching of the silicon dioxide that was oxidated on it, and figure 5 shows the photoresist strip being stripped, and figure 6 shows a clean wafer again, and figure 7 shows the dopant oxide deposition, and figure 8 shows the cap oxidation, figure 9 the drive-in, and figure 10 shows the oxide strip, which is ready for the next step. So next we are going to discuss about what is a source drain formation. So a source drain formation is a method of forming a field effect transistor device which includes forming a diffusion facilitation layer on top of a semiconductor substrate. Next, forming a doped, raised source or drain layer, which is called as RSD, on the diffusion facilitation layer. Next, removing a portion of the diffusion facilitation layer corresponding to the region directly above a channel region of the FET device. And performing an anneal so as to define abrupt source and drain junctions in the semiconductor substrate, wherein dopant atoms from the doped RSD layer diffuses within the diffusion facilitation layer at a fast rate than with respect to the semiconductor substrate. So now we can see a simplified diagram about the processes involved in the source drain formation. So first off, we have the spin-on dopant, and next we have the soft bake process. Next is the drive-in or diffusion process. Then fourthly comes the visual inspection, and lastly is the oxide measurement. So we will be discussing about each and every one of these processes briefly in the next slide. So now let's look at spin-on dopant process. So what happens in the spin-on dopant process? A rapid thermal diffusion, RTD, of phosphorus has been investigated using a spin-on dopant, SOD, deposited on a silicon wafer, and it is then placed as a dopant source in proximity to a processed silicon wafer. In such process, the efficiency of doping is affected by the amount of phosphorus supplied from SOD to the processed wafer. Moving on, let's talk about soft bake process. So what is a soft bake process and what happens in a soft bake process? So soft bake process is a low temperature bake, which is anything under 100 degrees Celsius, to which the wafer is subjected after deposition of photoresist, aimed at the volatilization and solvents in the resist and its solidification. It is typically carried out using a hot plate in ambient air. Moving on, let's look at what happens in the drive-in process. So it is a high temperature operation, which is anything above 800 degrees Celsius, which is performed on semiconductor wafer in an inert ambient. This causes motion of dopant atoms in semiconductor in the direction of concentration gradient, which is known as diffusion, and it is used to drive the dopant atoms deeper into the semiconductor. So now we have come to visual inspection process. So let's see what happens in visual inspection. So the visual inspection of semiconductors is performed using a camera mounted on a microscope. The sample wafers are examined by a computer vision algorithm and rapidly scanned. The algorithm is then designed to quickly detect and classify any defects. So to make our world easier, we are using an automated visual inspection system, which is an image processing technique for quality control and production line automation. This is to improve the yield rate and reduce manufacturing costs. This inspection device is widely installed in all the design, layout, fabrication, assembly, and testing processes of production lines. So we have finally came to the last process, which is oxide measurement. So we will refer to the next slide where I've provided a chart which shows us the various methods we can use to determine the oxide measurement. So we have reached the last slide of this segment. So in this slide, I will be explaining about the various types of methods we can use to find the oxide measurements. So we have 4 methods here, which is ellipsometry, reflectometry, color charts, and process uniformity. So first off, let's start with ellipsometry. Ellipsometry is commonly used to measure dielectric thin film refractivity and thickness. Reflectometry has 2 different tools to help us find our desired measurements. So spectroreflectrometer measures the reflected light intensity at different wavelengths, where the spectrophotometer is also used to measure oxide thickness. Moving on, we have color charts. After the oxide is grown, the color of the wafer surface might change. So the color depends on the film thickness, refractive index, and the angle of the light. Color charts are very convenient to measure film thickness. Although it's no longer used in advanced IC fabrication, they're still a useful tool to estimate the oxide thickness quickly and to detect non-uniformity. So this method is used to find an estimated value, nothing specific. So the process uniformity. The uniformity of the oxide thickness is routinely measured during processes, development, and for statistical process control monitoring, SPC. So I hope the information that I've shared is sufficient. Thank you.
Hello and Assalamualaikum. I am Afika and I'll be continuing about photolithography process. Have you guys seen this photo film? Maybe we are not in the era of using this, but we definitely know its function. It's realistic to imagine how images are being transferred to this photo film. When we take picture, images will form on this photosensitive photo paper. Now, with the same concept, we might want to change our perspective to the things you are learning. It's CMOS fabrication. Have we wondered how actually the tiny fantastic pattern form on this silicon wafer? Well, understanding photolithography process will make this sense. First of all, what is actually photolithography? The word photolithography is originated from Greek words, which are photo, which means light, litho, which means stones, and graphy, which means print. So photolithography process is a patterning process that transfers a designated pattern from a mask or reticle to the photoresist on a wafer surface. In short, photolithography is printing a pattern using light. Based on the exact run-cut sample given, 4 repeated steps of photolithography will be needed in this fabricating process. The 4 masking steps which involve photolithography are, firstly, source drain masking, which is after the wet oxidation process, and secondly, the gate masking, which is after diffusion process, and thirdly, contact masking, which is after dry oxidation, and fourthly, the metal masking, which is after metallization. So overall, the basic things we need to know about photolithography is that firstly, it is the most important process in IC fabrication. Photolithography consumes a lot of time, which take about 40 to 50% of the total wafer processing time. Secondly, photolithography contains of several other steps, and the main processes are coating, exposure, and development. And thirdly, among the important components of photolithography are photoresist and photomask. Next, I'll introduce you guys about photoresist. Photoresist is a photosensitive material used to coat a wafer temporarily and then transfer an optical image of a chip design to the wafer surface. In short, photoresist can be understood as the silicon's protector from the UV light while the pattern is created. As its name, photoresist will resist UV light, and photoresist consists of four basic components, which are polymer, sensitizer, solvent, and additives. Photoresist is categorized into two types, positive and negative. In a simple way, positive photoresist maintains the pattern defined by the mask, while negative photoresist distorts the photomask pattern like this figure. Positive photoresist often used in advanced MOSFET fabrication as it has high resolution at scale of nanometer. Basically, these are the photolithography process steps. There are 8 steps altogether. For the first step, wafer cleaning, which is very important to remove contaminants from previous processes. Then, preparation, or commonly known as priming. Most common primers used is HDMS. Next, photoresist coating process. Actually, the photoresist were coated using spindle, which use centrifugal force. Moving on, alignment and exposure process is very important as it determines the success of the pattern transferring. Basically, all baking processes such as soft bake and hard bake are literally baking process where the substrate will be heated on a hot plate with temperature around 100 to 130 degrees Celsius. PEB process will reduce the standing wave effect caused by the exposure process. And lastly, hard bake will strengthen the photoresist. So, this is the visualization of the process, and this process is being done in the photo bay. To conclude, to achieve a successful photolithography process, these requirements, which are high resolution, high sensitivity, precise alignment, and low defect density, must be fulfilled. And that is all from me. Thank you.
Hello and Assalamualaikum. I'm Nurin Ishira. I will continue the presentation on the metallization process. Basically, metallization process is a process by which the various components of ICs are interconnected by a metallic layer as well as connection for external devices. This process produces a thin film metal layer that will serve as the required conductor pattern for the interconnection. So, metallization is the final step in the wafer processing sequence. It starts with metal deposition, where aluminum will be deposited, then it will undergo metal masking and metal etching. After the final photoresist stripping, all the CMOS fabrication steps are completed. In selecting the material for the metallization, there are some desired properties for the process, which is low resistivity, mechanical stability, which is good adhesion and low stress. Next is surface smoothness, and also should not contaminate device or wafers. Thin aluminum is the most widely used material for metallization, but other materials also can be used such as aluminum silicon alloy, aluminum chrome alloy, and also pure copper. For aluminum, it can be easily vapor deposited, has good adhesion to silicon dioxide, low contact resistance, and also easy to pattern. However, due to its low melting point, which is 660 degrees Celsius, it interdiffuses into silicon to form aluminum spikes, where it can puncture through the doped drain source junction, causing shorting to substrate silicon. This effect is called junction spiking. To prevent this effect, 1% of silicon is added to aluminum to form alloy. Therefore, it can undergo thermal evaporation with a large difference of the melting points. Aluminum is a polycrystalline material which consists of many small monocrystalline grains. When electric current flows through an aluminum, a stream of electrons constantly bombards the grain, and it starts to move down, causing electromigration. High current and high resistance would generate heat and eventually cause breaking of aluminum line. By adding 0.5% of copper, it can help to improve the resistance of aluminum migration, because copper atom is larger and it can hold aluminum grains, preventing migration. The last one is pure copper. It has lower resistivity than aluminum copper, which is 1.7 micron ohm cm. It also has higher electron migration resistance because copper atoms are much heavier than aluminum. However, copper does have problem of addition with silicon dioxide in high diffusion rate which can cause heavy metal contamination and lead to malfunction of the ICs. Thus, a barium metal such as tantalum needs to be deposited before depositing copper. PVD is a deposition process that vaporizes solid materials either by heating or by sputtering and recondenses the vapor on the substrate surface to form a solid thin film. Comparing PVD and CVD processes, PVD uses solid sources while CVD uses gases or vapor precursors. A CVD process relies on chemical reaction on the substrate surface while PVD uses physical forces. CVD film has better step coverage while PVD film has better quality, lower impurity concentration, and lower resistivity. There are three methods used in metal PVD processes, which is thermal evaporation, electron beam evaporation, and sputtering. The first method is thermal evaporation. Throughout the process, the system needs to be under high vacuum, about 10 to the power of -6 torr, to minimize residual oxygen and moisture. A red-hot tungsten filament heats up the aluminum charge, melts it and vaporizes it in the vacuum chamber. When aluminum vapor reaches the wafer surface, it recondenses and forms a thin layer of aluminum film on the surface. Next method is electron beam evaporation. It replaces filament heating, which can cause contamination and poor step coverage. A beam of electrons, typically with energy of about 10 keV and currents up to several amperes, is directed at the metal in a water-cooled crucible in a vacuum chamber, and it heats the metal to an evaporation temperature. The last method is sputtering. It involves energetic ion bombardment to the target plate, which physically dislodges atoms from the solid metal surface and are thrown into the vacuum in the form of a metal vapor. Then these atoms are deposited onto the substrate surface to form a metal thin film. Argon is the most frequently used gas for sputtering processes because it is inert, relatively heavy, and abundant.
Hi, I'm Shafika and I'm going to present to you about etch process. So when we look at this picture, we can see that the silicon wafer is very flat, right? But when we look at MOSFET here, we look closely at the MOSFET, we can see they have drain here, they have this, I can say they have dig a hole. How can we dig a hole on this silicon surface? So we use a technique called etch. So what is etch? Etch is basically a process where we use chemical solution to dissolve materials on the wafer surface and achieve device and circuit requirements. We have two types of etch. We have wet etch and we have dry etch. So the byproducts of the etch process will dissolve in the etchant solution. This goes for both wet and dry etch process. One of the process in dry etch is plasma etching. Dry etch is an anisotropical etch process, which means it has a small bias. This explains why for a semiconductor with size features smaller than 3 micrometers need to use dry etch. When we talk about what type of etchants that we need to use on what materials, on what type of surface that we're going to use it, we need to consider the selectivity and the isotropy of the etchants and the surface. I'm going to talk more about this on for the slide because it's not really a picture that can show you the difference between these two. Okay, so as you can see, we have four types of wet etch. We have oxide etch, we have silicon etch, we have nitride etch, and we have metal etch. So we call this oxide, silicon, nitride, and metal etch because it actually defines type of material of this surface wafer that we use for the etch. But basically, the process of the etching is just the same for all of them because it's basically just oxidation, and then we dissolve it, and oxidation, and we dissolve it for a wet etch. Okay, for the first one, we have oxide etch. So what is oxide etch happens in source drain transformation and third masking when we look at the whole process of MOSFET fabrication. Alright, so oxide etch, when we do oxide etch, we're going to do etching on an oxide surface. So we're going to, the etching that we're going to use is basically HF, which is hydrofluoric acid. So we either will use buffered oxide etch, which is just a mixture of hydrofluoric acid and NH4F, which is ammonium fluoride, or we will use diluted HF, which is DHF, which basically just HF with a little bit of water solution, right? While we have to use buffered oxide etch and diluted HF instead of just HF. It is because the process of the etching is going to happen so fast that we cannot really control it. That's why we need to use BOE and DHF so that we can better control the etch rate and also uniformity of the etching. So this is the chemical equation of the oxide etch. Okay, you can see the next one is silicon etch. As you can see, when we look at the whole fabrication process, we can see that silicon etch happens in first masking and also second masking of the fabrication process. Okay, so silicon etch is going to happen on a pure single crystal silicon surface, and the etchant that we're going to use for silicon etch is hydrofluoric acid and also nitric acid. So because I said earlier that the process is basically just the same, it's just oxidation and then dissolve, that's why we're going to use hydrofluoric acid. And for nitric acid, we need to use it because this time we're going to apply this etch on a pure silicon etch, which means that just now we applied on silicon dioxide etch. That's why you can just dissolve it right away. So that's why we need to use the nitric acid here in silicon etch so that we can actually first oxidize the silicon etch and form silicon dioxide, and then the fluoric acid, hydrofluoric acid, going to dissolve the silicon dioxide, and the process going to repeat itself until they reach the depth that they want. As you can see here, this is the chemical equation. Okay, for the next one, we have nitride etch. As you can see, nitride etch doesn't really happen in the whole fabrication MOSFET fabrication process, so I won't really go deep into this one, and because we're running out of time, nitride etch happens in isolation formation process, and isolation formation process happens if we want to manufacture bipolar transistor based IC chip. So I will use this picture that I talked earlier to tell you a little bit about selectivity. So as we can see on this picture, from the first picture we have this nitride layer and also silicon layer, and from the second picture we can see that the nitride layer is gone. So this condition where we want to etch only the nitride layer, this is what we call selectivity, and selectivity is something that wet etch is very good at. The next one we have metal etch. Metal etch happens during the port masking. So the etchant that we use for metal etch is acetic acid, water, nitric acid, and phosphoric acid. So we can see the concentration of all of those acids because the concentration of the etchant is very important to determine the etch rate. Then the process is basically acid oxidize the metal and the metal oxide will form, and then the byproduct dissolve the metal oxide, and step 1 to 3 repeats. The oxidation and reduction happens simultaneously. It uses the redox reaction just the same as any other etch before this. Okay, for the last one, we have plasma etch, also dry etch. Plasma etch is anisotropic due to ion bombardment, which means they are small bias and less CD loss than wet etch. So why do we call this one dry? It's because we use gases, chemical etchants, and in wet etch we use liquid instead of gas, so that's why it's called dry, and they create volatile byproduct that will be removed just the same way as in wet etch, where the byproduct will be removed from the wafer surface, so we don't have to worry about the byproducts sticking on the surface. And factors affecting the etch is plasma generates radically free electrons that will increase chemical reaction, and muon bombardment on the wafer surface that physically remove the material from the surface, or the chemical bond increase the chemical rate. So when we actually increase this chemical rate, what will happen is they will impact our etch rate, and that will impact our etching process. The MOSFET fabrication process is, the first of all, we have wafer preparation, and next we have first fill oxidation, and we have source drain masking, and then source drain formation. After that we have gate masking, and then gate oxidation dry, and then we have contact masking, we have metallization, and lastly we have IV categorization.
Lastly, to summarize the overall process flow from the run cut, like mentioned by Shafika just now, we provided a visualization of the process flow. Firstly, the wafer is prepared, then the first oxidation process happened. Source and drain masking, wafer etching and diffusion, strip photoresist and etching, gate masking, gate oxidation and contact masking, metallization and metal masking, and lastly, IV characterization. CMOS fabrication can be accomplished using either three of the technology, which are N or P-well technology, twin well technology, and silicon on insulator technology. With that, I think that is all from our group. Thank you.